It is a real pleasure to have Neil Cornish with us, visiting from Bozeman, Montana. Neil is an esteemed colleague in gravitational wave science. He's very, very well known, like throughout the world, about all the things, the cool things that he's worked on, and he's done. But you know, his timeline starts in Australia. That's where he did his undergraduate and his master's in physics. Then he decided to switch continents, went to Toronto to do his PhD. And following that, he again decided to switch continents. He was a postdoctoral fellow at Cambridge with Stephen Hawking. And then he clearly liked North America quite a bit, so he came back to North America. He was a postdoctoral fellow at Princeton University, where he worked with David Spergel. After Princeton, he went to Montana, where he started as a faculty, and he's now the Regents Professor in Physics at Montana State University. He's also the director of the Extreme Gravity Institute at Montana, and an APS fellow. His interests are pretty diverse in physics, I would say, but he's well known, at least to me, for his work in gravitational wave science. And he was, of course, among the very first people who analyzed the data for GW150914, the first gravitational wave detection. And most recently, the detection of at least the evidence, as we discussed, for the gravitational wave background using pulsar timing arrays. And he's also a member of the NASA Science LISA team that hopefully we'll be hearing all of everything during this talk. So Neil,
thank you very much, Phyllis. All right, thank you for the invitation. It's great to be in Arizona. Yes, it was actually interesting with the the first detection in the ground-based band with LIGO, and then the evidence for, we won't quite call it a detection in pulsar timing. I think we did a count. There's 10 people were authors on both sets of papers, and I'm hoping now, 10 years or so from now, maybe a bit longer actually, I'll actually get to make it 3 out of 3 with the first detections from LISA, the future space-based detector. So that's my goal. Today I was overly ambitious. I've actually I couldn't quite decide what to tell you about. I want to tell you everything that's going on in gravitational waves, so the recent history and where we're heading. And I also wanted to cover everything, so ground-based, space-based, and using pulsars. So I've actually put 3 talks together, which is impossible to cover. We'll see how it goes. But anyway, let's get going. All right, as Vasilis mentioned, we go back now to September 14th, 2015, and we had just turned on the advanced LIGO detectors, and we got this beautiful signal arrived right away. Actually, still one of the loudest signals we've received. Didn't wobble the Earth quite that much. It was vastly exaggerated, it says. First coming in and striking the Livingston detector, and then, because coming up from this direction, and then eventually reaching the Hanford detector in Hanford, Washington. And we got these, this fuzzy reconstruction here was one that my group did, and we had that the day that the signal arrived. And my son had been asking me for years, because he asked me what I did for a job, right? And I said, well, we're trying to detect gravitational waves. And each day, or about once a week, he'd ask me, well, have you found them yet? Year after year, it just went on. No, we haven't found them yet. And then as soon as the signal came in and we got the analysis, I went, I wasn't supposed to tell anyone, but I figured I could tell someone that was a middle schooler. So the first person I told, actually, I think my son and my daughter, who's here today, I showed them the results that we just got that day from this detection. So it was extremely exciting. And finally, I wasn't a loser anymore, because we finally found what we were looking for. So, but really the history of gravitational wave detection goes back long before that 2015 signal. In the early 70s, several people, including Ray Weiss, were looking at the possibilities. How might we go about detecting gravitational waves using interferometry. People like Bill Press and Kip Thorne were already thinking about, well, if we have these detectors, what astrophysics can we do? Which was pretty bold because there was not even a detector design yet. In 1975, a NASA report on what to do with the space shuttle, the Weiss report, Weiss, Bender, Pound, and Misner came up with the idea of the LISA mission. And Pete Bender has continued to work on it. I don't know how old Pete is now, but he's still going, still a member of the LISA NASA science team, and I see him regularly via Zoom. So yeah, he's still at it. I think he must be in his 90s by now. Very influential papers in this volume. And then in pulsar timing, Steve Detweiler talking about using pulsars to measure gravitational waves in the late 70s, and then the method of how to actually tell it's a gravitational wave from Ron Hellings, who was the first student in gravity at Montana State University. And George Downs wrote this paper on how to do the detection. So a lot of this stuff happened in the 70s. And just to, if any of you are like getting started out right now, a lot of times, if you want to do something bold and really transformative, you have to stick at it. So 40, 50 years later, you get your payoff. And it sounds daunting, but that's what it took to make this happen. And Ray was still there for the detections, and I hope Pete lasts forever.
A Nobel Prize.
Yeah. So, wow, there's a real interesting Zoom slow delay here on bringing up slides. But anyway, so for the gravitational wave spectrum, I'm going to be trying to tell you a little bit about pulsar timing, space detectors, and ground-based interferometers. I'm going to start here on the ground. And the basic principle of how we detect gravitational waves is something that even a theorist can understand, like me, originally a theorist. So we've got the plus and cross polarizations. If you have a ring of test masses, they're being alternately stretched and squeezed as the gravitational wave, say, propagating into the screen would deform this ring. And especially if you look down on this bottom panel, this now is with time running this way, you see alternately one arm of a L-shaped detector would be stretched and then compressed, and the other one stretched. And so the idea is, if you can measure this change in distance between free moving masses, then you can detect gravitational waves. Of course, putting all that together, again, this is the theorist picture of how LIGO works. You have a laser, you send light down one way, bounces off a mirror, comes back, and then you recombine it. You either come back at constructive or destructive interference. LIGO sits just off a destructive interference fringe, so just if a little bit of extra light floats through, you can tell. And so we're actually not measuring, the wavelengths of the light are like a millionth of a meter, but we're measuring changes, phase shifts of not half a wavelength, but 10 to the minus 13 of a wavelength, right? So tiny changes in the interference pattern is how we actually detect. So we've got our two detectors in the US. We've got the one not too far from where I live in Hanford, Washington, and then down in the swamps of Louisiana, we have one just outside of Livingston, Louisiana. And, the fractional distance measurement we're making over these 4 kilometers is equivalent to measuring the distance to Proxima Centauri to the width of a human hair, right? That's the fractional change in distance that we're tracking. It's 1/10,000th the width of a proton, which is just a reminder, it's a lot smaller than an atom. So remarkable instruments. In fact, when you look at what limits the ability to measure, focus really on this purple curve, which is here. This is quantum noise. So fundamental quantum noise. These other things we call facility noise, like seismic, gravity gradients, noise in the coatings on the mirrors. All of those add up to, take us a little bit worse than the quantum limit. But LIGO really is a 4-kilometer long quantum device. And just threw this in on the quantum noise. So at high frequencies, our ability to measure the fringe shifts, you want more photons, right? So the noise scales inversely with the square root of the intensity. So you just want to up the intensity, bigger and bigger lasers. We have really big lasers now. Input lasers are hundreds of watts. We build up megawatts of laser power, right? So huge intensity. I don't know how many photons that is, but it's a large number. So you want enormous intensity so that you can measure these tiny changes in the distance between the mirrors. However, there's a problem, and that is light exerts radiation pressure. And that radiation pressure pushes the mirrors and causes low frequency noise. And so the more powerful you make the lasers, the worse you make the low frequency performance, right? So there's this trade-off, and this is known as the standard quantum limits, the point where these two meet in your detector. And just recently, there was all of these, this was just last week, you might have seen a bunch of news stories if you happen to have news feeds that include science, and it talks about LIGO breaking the quantum limit, right? So we've actually exceeded now this this limit. Yes, you have a question?
Yeah, did you say megawatts?
Yes.
Sorry, that's hard for me to comprehend. I mean, seriously, continuously running megawatt laser in the small cavity is an awful lot of energy.
It is. I mean, well, it's a big cavity. It's the biggest man-made vacuum system on the planet. But no, the thing is, like, the input laser's a couple of 100 watts.
Thank you. That's what I'm.
But right. So we're running a couple of 100-watt laser continuously, which is still a big laser, but it's getting stored in Fabry-Pro cavities. So we're building up the light because it's stored for many, many, many bounces. So it's stored laser power in there as megawatts.
Stored laser energy.
Energy, that's right.
Yeah, power is.
Right, stored laser energy.
Yeah,
in there,
that's
right?
what I'm confused by a statement of megawatts, which is a very different thing.
Well, I guess they mean by the flux coming through any particular slice at any moment, right? So, but it's, you know, early on we had a time when one of the mirrors tilted and the beam went up and it just sliced right through the supports of the mirror at the other end and went crashing down. So anyway, these stories talking about LIGO breaking the quantum limit, what actually was going on, and I don't actually understand how they do this. I know they have a squeezer. I don't know how you squeeze light. It's quantum squeezing. So you've got the Heisenberg uncertainty principle, the uncertainty, say, in position, times the uncertainty in the momentum. It's got a greater than h bar. Well, it's the position uncertainty that's creating the noise at low frequencies, this radiation pressure noise. It's the uncertainty in position that limits our sensitivity at high frequencies. So what they've implemented is something called frequency-dependent squeezing, such that they squeeze the uncertainty ellipse, so it's very small uncertainty in momentum down at this end of the detector band, but then a very large uncertainty in position. And at this other end, they made it so it's very small uncertainty in distance and a very large uncertainty in momentum. I have no idea how they do this, but they have a 300-meter cavity that injects squeezed light into the system to put into this quantum state. I'm going to learn how they do it because it's really cool. But so it's now, we can now exceed this so-called standard quantum limit. Standard quantum limit is derived for a round error ellipse. And so that's increased the sensitivity quite a bit. As we go through from the various different, here's the years here, the different observing runs. The first observing run when we got our first detection of a binary black hole merger, our second observing run where we actually picked up our first binary neutron star merger, and then the third, you see there's been a progressive increase in the range. The range is calibrated for binary neutron stars of 1.4 solar masses. It's just a sort of our sort of standard candle. Because the sensitivity goes as mass to the 5/3 power, we're way more sensitive, like we can see much further for black holes. But black holes come in all sorts of different masses, whereas neutron stars are all about the same mass. So we kind of quote the range for neutron stars and just multiply this by a big number for how far we can see black holes. We're currently in the fourth observing run right now. LIGO was designed to be somewhere between 160 and 190 megaparsecs. Virgo, the Italian detector just outside of Pisa, was supposed to be operating at around 80 to 115, and the Japanese detector was supposed to be somewhere maybe up to 10. Unfortunately, LIGO's been sitting more around the 160 level, 160 megaparsecs, except I got an email yesterday saying that they, for the first time ever, reached 170. So they're slowly kind of cranking things up and figuring out gremlins and improving things. So, maybe we'll get up to 190 by the end of the run. Virgo had a few things break. They're hoping to rejoin at about 40 megaparsecs, which is what they were doing in 03. And Cagra's still struggling. They're hoping to be joining in spring at 10 megaparsecs. It's not easy to make things. Into the future, we hope to be, doing much even better. So there's progression. And if you look at what that means over time, these are all of the different detections we've made so far. And here's the mass and solar masses on the y-axis, and this is just the order the events arrive. The orange dots are things we think were neutron stars. The blue dots are things we think are black holes. And you can see that this is all the detections we had during the first observing run. These were all we had in the second observing run. And then the third observing run was broken into 2 chunks with a gap in between to tune things up a bit better. And so we got way more in the third. And we're in the progress right now. It's been going since, I don't know, sometime late summer, the 4th observing run. And you can go and look at the website. And these are the public events. I screen grabbed all this on Friday, and there's been another one since then. These are public alerts. And possible source, sometimes we retract them because turns out just to be junk. But mostly they're black holes. We've had a few black hole neutron star candidates and no more binary neutron stars so far in 04, at least public ones. And here they all are, scrolling along. So it was like something of order 60 so far that we are pretty confident on. So we've added about another 60. I think it's probably more than that once we dig a little deeper. Probably added up maybe another 100 or so at this point. So that's what's been going on. So we're really starting, things that used to win a Nobel Prize are now happening, once every day or two. That's progress. And what we're able to do with this, as we went from what we called the Gravitational Wave Transient Catalog 2, which was everything from the first 2 observing runs, we were able to kind of make this inference. This is the rate of mergers per cubic gigaparsec per year per, and here's the mass. And so sort of noticing maybe some features, maybe a cutoff, maybe a mass gap between black holes and neutron stars, and maybe a bit of a bump at around 35 solar masses. So we see this now with the full catalog that we had. And so as time goes on, this is going to get much better resolved. So we'll get a better idea about the, rates of mergers and what the, how the rate depends on the black hole masses that are involved. In terms of spins, so far we're not really seeing much sign of spin. There's the spin that's parallel to the orbital angular momentum, so the intrinsic spin of the black holes. This is this parameter here. It's a number between -1 and 1. And this is the in-plane component. So this would be the component of the spin orthogonal to the angular momentum, right? And really not much evidence that we've seen much of this. This causes orbital precession. So it's right now, we're not really seeing much in the way of spin, which would tell us something about the processes that cause these black holes to form. And what happens with spin, if you have misaligned spin, so here's a sort of smallish black hole and a biggish black hole, the total angular momentum, the sum of the 2 intrinsic spins and the orbital angular momentum, that quantity, the direction that points is essentially constant, but then there's a precession, there's a trade-off between, and you can see that it means that the orbit changes its orientation with respect to us. And gravitational waves are most powerful when you're looking face on, when the system's going around like this. Edge on, you don't see very much radiation. It's a quadrupolar kind of pattern. And you see that because the orbit is modulated, it tilts towards you, gets louder, tilts away, gets dimmer. We haven't seen this yet, really, but we're hoping to. One of the reasons we haven't seen it, this is what a signal from this is all the cycles of a non-spinning black hole viewed face on. This is what it looks like for a spinning black hole if you observe it face on. They look pretty much the same. If you observe it edge on, you see all these modulations. But, think of a wobbling plate. You can't tell it's wobbling if you're watching it, face on. So we've mostly only been seeing ones that are face on. The reason is, come on, advance. Here we go. There's a selection effect. The emission is much stronger from systems that are face on. So we mostly only see systems that are face on. Edge on has a way less power by over an order of magnitude. So there's a huge selection effect that says we're most likely to see face on systems. And also we're much more likely to detect massive systems, very massive systems. which means that they are much lower frequencies and they merge very early in the sensitivity band of the detector, so we don't get very many cycles. So the wave doesn't get through many cycles, so we don't get to see the precession. So these things are working against us from being able to see all the spin effects, but that'll get better with time.
Can I ask a question at this point? So if you have black holes of very different masses,
Right.
You're saying you have the possibility
Mhm.
of injection of a jet of gravitational radiation in some random direction.
Mhm.
I don't know how tightly correlated it is. Is that something that's factored into those diagrams? Could you
Yes.
see something like that?
Right. In fact, there is, in particular, when they finally merge, there's sort of an averaging of, if it's like a quasi-circular kind of binary, you don't really get a net momentum in any particular direction. But when they finally go to plunge, that breaks the symmetry, and you actually then get a jet, and it actually jets the black holes off at actually a decent fraction of the speed of light. And so people have been looking for evidence, for black holes that might have been ejected, like massive, supermassive black holes that actually might have merged and got shot out of their galaxies and things like that. We haven't, it's included in our modeling, and we can kind of predict what the kick would be, but we've not got any like counterpart kind of information showing us the kicks or anything like that.
You see observational evidence for that in LIGO?
Well, it's sort of built into the waveforms, but we don't really see it as we don't see like the system kind of like getting shot out.
I don't mean that, but is there a directional anisotropy associated with the gravitational wave emission that you?
Well, we're not seeing anything to do with this final. Well, again, we haven't been seeing. We've been mostly seeing sort of face-on systems and this sort of thing, but we should start seeing more of the edge-on type effects, and people have like considered whether we'd actually see, in the ring down, the evidence of this kind of kicking happening. So one of the problems that we're suffering from right now is we don't have enough detectors. We really only have two, like unless all the detectors are comparable in sensitivity, they're not very effective, right? So we need multiple comparable sensitivity detectors. We have 4, but 2 of them aren't anywhere close to the LIGO detectors in terms of sensitivity. So really we only have 2 detectors. With more detectors, it gives you much better sky coverage, but it gives you much better source localization, allows you to measure polarization. Unfortunately, the LIGO detectors they're lined up, so their polarization, they measure the same polarization essentially of the gravitational wave. They only measure one of the polarizations. If they'd been put 45 degrees rotated from each other, it'd be way better, but it's too late to change that now. It was a bad idea. I know why they chose it the way they did, but they just were concerned about detection. They thought it would help detection, but it really messes up being able to infer the system parameters. So it was a bad choice. But anyway, but we just need more detectors to fix that. It also allows us to be much more robust against various noise transients. Things go pop in the detectors occasionally, right? So if we had more detectors, we'd be able to better distinguish between noise and signals. And especially that's important for a novel source, something that we don't have a good model for, because then we just really have to rely on it being something we're seeing simultaneously in all the detectors. We don't necessarily have a model for exactly what the wave should look like. If you have a good model for the wave, like we do with black holes, then you can make a detection with a single detector. So we've now had multiple LIGO detections that are from a single detector when only one was running, because we're so confident about the shape of the signal that we can tell it apart from noise. But for a novel source, that wouldn't be possible. And just to go through, here's the current network. We've got the Hanford Livingston detector, Virgo in Italy. It's approved by the Indian government. That's going to be one of the LIGO detectors, and we have a spare. It's going to get placed in India. They're going to start construction soon. And we have the Japanese detector. And each one of them, if you look at the antenna pattern coverage, the 2 LIGO detectors overlap pretty closely. Virgo really gives us quite a different pattern. India, and then the Japanese detector, but their usefulness will be greater once they're all similar in sensitivity. With 2 detectors, you can localize a source to a ring on the sky just from the time of arrival. So that gets you a ring on the sky. With 3 detectors, you get couple of different rings, and when those intersect, you get 2 points on the sky, and with 4, you just get a single point. So multiple detectors really allow us to triangulate the direction the source is coming from. So this is what it looks like. If you just have one detector, you end up with a sky map like this. Most of the ones that were rapidly scrolling by you all look like this. It's because we've got currently 2 detectors. So this is just the sky ring for that particular source. And then if we happen to have Virgo, we can narrow it down like this. And this is what happened with the first gravitational wave from binary neutron star. And we were lucky enough that in addition to the gravitational waves, Fermi picked up a little gamma ray pop at the same, just after the merger. And then, you know, a good fraction of the telescopes on the planet got turned looking for this, and they found the counterpart, and that was wonderful. But that was only possible because Virgo was operating well enough at the time that even though the signal was not detected in Virgo, it could have been if it had been anywhere else on the sky. So it told us where it wasn't. So that allowed us to then narrow down from the LIGO detection where it actually was. And then we also had the Fermi localization, which wasn't great either, but put it all together, it got us down to a few enough galaxy candidates that we're actually able to find the galaxy that this was coming from. And, you know, if you look at the predicted rate, here's a paper that was making predictions about how many of these might we see with, say, the Zwicky transient factory, joint detection of a kilonova with the LIGO. And the predictions, if you extrapolate to 02, we shouldn't have seen any. In 2017, it just shouldn't have happened. It was just extremely lucky. The rate should have been 0. We should have seen some in 03, we didn't. We should see some in 04, we haven't. I'm not sure we will unless Virgo gets going. And it doesn't look like it's going to get going at enough sensitivity. So I don't think we're going to see any in 04. So I think the time between the first electromagnetic counterpart and the next one's going to be 10 years. It just shouldn't have happened. 2017 was a freak. So I don't think it's not going to become a regular thing for another several years. So it's going to be great when we can do more of this multi-messenger astronomy, but it's just not going to be a common thing for a while because we don't have enough detectors. One thing that I'm really excited about for the future and looking at the history of astronomy are things that go bump in the night. If you think back of, you know, the story is you build a sensitive instrument and you discover things you didn't know, you know, you weren't looking for, like cosmic radio waves, X-ray binaries with the first sounding rocket X-ray experiment looking for X-rays from the moon, but they instead found X-rays coming from SCO-X1. Microwave background, at least the guys that found it didn't know what they were looking for. Other guys were looking for it. Gamma ray bursts with the satellites monitoring nuclear test ban treaty, radio pulsars, little green man, and then even more recently, fast radio bursts. So I'm hopeful that we're going to find things that aren't predicted, and we have techniques to do that. One that my group developed, this one called Bayes wave, another one that Sergei Klemenko's group out of Florida developed. And these are methods where we can actually detect signals. These are, so the first signal was detected without any templates. They weren't running. The search wasn't running. The only searches that were running were these ones based off agnostic signal reconstruction. And so the first gravitational wave ever detected was detected using methods that could detect arbitrary signals. They have to be relatively loud, like the one, that first detection. So with time, this is a comparison of the reconstruction from my group that we got on that day, and then using templates, and they're in very good agreement. So we're actually able to, you know, pull signals out without any model. So if something unusual does show up, it's these techniques that will allow us to actually detect, you know, things that theorists haven't predicted. But again, they have to be relatively loud for us to be able to tell them apart from instrument noise, and would help to have lots of detectors, because that's going to be a lot easier to distinguish from transients in the detectors. So that's one of the things that most excites me about the future. I'm really hoping we're going to find something that no one's predicted.
What's the feature of your template? It looks like a ring down from this distance.
Well, there is a ring down, but the template doesn't have that in it. It's just it's actually based out of a coherent sum of wavelets that can produce you know, you can model anything with a collection of wavelets. And so it's it uses the sparsest representation it can of the data using wavelets. And, you know, it's able to see all the features, including, so when I was first looking at this, I was like, wow, this signal looks just like what those people that were doing numerical relativity and producing, you know, black hole merger waveforms looks exactly like that. It's got, you know, this big sort of ramp up, it's got the ring down, it was all there. So, you know, we were like, this looks like a black hole. And it wasn't until quite a bit later that we actually, then the pipelines weren't quite ready, right? The detector went online and the analysis pipelines were still getting ramped up. It was during the engineering part of the run before we actually turned on officially. And so they didn't yet have the search going for high mass black holes. So it was discovered other ways. Going forward, there are plans to develop various different upgrades to the existing instruments, like A+ would probably be running by about the 05, fifth observing run, Voyager, which is still using the current site, and then much more bold new plans, Cosmic Explorer, which is this one. It's actually on the Earth, not in space, but and Einstein Telescope, which is a European effort. And these will basically take us out. So every single neutron star merger, every single black hole merger in the entire universe could be observed by these that are happening. And those happen every, you know, few minutes. So you'd have tens of thousands of events a day is where they're heading in the future. And I'm hoping that in amongst all of that, there'll be some unexpected things, not just black holes and neutron stars and black holes and neutron stars merging together. So in my lightning tour here, heading down into the nanohertz regime. So this is up in the acoustic range where you can actually, let's go and listen to the detectors. Here's down where you've got to be patient because the cycles are sort of like, you know, 1 over a year, you know, like the frequencies are, these are periods of years. So you have to observe for a long time. And we do that using millisecond pulsars. And the idea is nature's provided these very regular lighthouse beams that sweep across the Earth. And some of the best timed pulsars are competitive with atomic clocks in terms of their regularity of their pulses. And so nature's provided this sort of galactic scale gravitational wave detector. We've built the receivers on the other end with radio telescopes, and gravitational waves change the light travel time of those pulses. So we see a little bit, the pulse might arrive a little earlier or a little later than it should have if there wasn't any gravitational wave. So that's the idea. There are various efforts. There's the European pulsar timing array using a collection of telescopes in Europe. In Australia, the Parkes pulsar timing array using the dish, famous from movies. And Nanograv, we have Greenbank, and we used to have our receiver, also famous from movies, but unfortunately it collapsed. We also use the VLA, and now we use other telescopes as well. But so we've got these international pulsar timing array where we eventually will get to joint analyses. But what we're expecting the signal to come from, emerging supermassive black holes. And as our sensitivity improves over time, we expect to kind of get in and start measuring the signal from this collection of supermassive black holes. We think there are probably tens of millions of these. And these are not like the LIGO case where they're just coming in and rapidly merging. These are hundreds of thousands or millions of years from merger. So they're sort of just sedately orbiting each other, and they're going to continue doing that for a very, very long time. So they're essentially sinusoids, each one of them. But there's a collection, you add up a whole bunch of sinusoids, you start getting something that looks like a stochastic signal. It's just a whole lot of sinusoids with different phases and amplitudes added together. So what we were expecting to see is essentially a stochastic background from these. And to detect that, we need an array of pulsars. And it's really the correlated pattern between how the signals in these different pulsars are disturbed by the gravitational waves. And here's all the Nanograv pulsars shown on an overview of the Milky Way. We've got 70 odd now. That correlation pattern that Hellings and Downs calculated is a unique fingerprint that you would get from gravitational waves and not other things. of how the delays in each pulsar should be correlated depending on how far apart the two pulsars are in the sky in angle, okay? So we have been collecting data, part of this collaboration. I don't actually touch the radio telescopes. I visit them occasionally, but other people do the radio astronomy part. I work on analyzing the data. They collected this data set for us. This is the 15-year data set. You can see that only some of the pulsars have been timed for 15 years. The colors correspond to which instruments and which receivers were being used. Most of them have been found more recently, so they haven't been timed for as long. So only some of ours are 15-year long. A lot of them are just a few years long. And we've analyzed this, and the predicted correlation is here, and what we're finding is this is the bin correlation that we're seeing, and we've done a lot of tests on this, and we believe we've got various calculations of significance, and we believe that we call it evidence for a gravitational wave background. The other pulsar timing arrays, we all simultaneously put out papers under an agreement, and they've all seen evidence as well. We are in the process right now of combining all the data sets and analyzing them all together, which, if this is really a signal, should increase the significance, right? Plus, Nanograv has 18 years of data already in the can. We've published on 15 years. It's going to take us another year or two to analyze the next 3 years, because it's a lot of work. It's not simple these are difficult instruments to figure out. So I'd say we have some evidence. I'd really like to see all this much more tighten up as we go forward. But this didn't stop a lot of people getting really excited. We had all of the press. Of course, all the press said that we detected gravitation. They all call it, we said evidence, and then everyone says, oh, they've detected gravitational waves. But, I guess they don't. So yeah, a lot of excitement about this. And also there's been a lot of excitement. There's this evidence paper in the last 4 months. So far, I just checked on Friday, we had 284 citations for that paper. But what's interesting is most of the citations are from sort of unemployed theorists at CERN and stuff, because the LHC hasn't really been producing anything different from the standard model. So they all have these early, exotic early universe ideas about what be producing this signal. So we really want to know, if this is a signal, what it's coming from. If it's coming from a population of massive black holes, it's not really going to be stochastic, and it's not really going to be isotropic, because it actually turns out to be dominated by a relatively small number, when you look at simulations, a relatively small number of very massive closer by systems. So we're not really in the central limit theorem here. It's really not quite stochastic. It's this is a bit hard to see, but this is in a given frequency bin in a simulation. One binary totally dominates, fails tests of isotropy. You take out one, it still isn't isotropic. You have to take out many. If you have at one frequency, we have to take out the 10 brightest signals in the simulation before it starts passing tests of isotropy.
Or is that it? Gigaparsec is close by.
Yes. So this here is this particular this is a histograms of this population that we were looking at in this particular simulation in this paper, which I forgot to put the reference on. And here's the frequency distribution of the signals of the population. Here's the mass distribution. Here's the distance distribution, inclination, and here's the signal to noise. And for detectable signals are the ones in red that could be detected individually. And you see that they're mostly at the high mass end, and they're mostly nearby. They're sort of around a gigaparsec. So we're going to be dominated by very, very massive, we're talking like 10 to the 10 solar mass or more binaries, and relatively nearby as far as cosmology goes, right? And there's not very many of those, so it's going to be highly anisotropic, and we'll be probably picking out individual systems. And interestingly, we found a hint of maybe a signal at 4 nanohertz. What was really interesting is Nanograv, completely independently from the European pulsar timing array, we both found exactly the same thing. Neither of us had enough significance, but I was actually, one of my friends, Stas Babak, who's one of the analysis leads, and I was co-lead on the Nanograv analysis. We both are in Lisa, and I said, Stas, are you seeing anything in your data I didn't tell him any frequencies, and he said, yeah, we're sort of seeing something. And then I said, well, is it sort of down at a few-ish nanohertz? He said, yes. And I said, well, what? He said, 4 nanohertz? I said, yes. And then I was like, if you show me yours, I'll show you mine. So we exchanged our results, just before publication. We're like, oh, looks like we're seeing, so it was interesting. We think, so I don't think there's not enough evidence for it yet, but we're both seeing something very similar. And maybe when we combine the data sets, which we're in the process of doing right now and doing the joint analysis, we'll see if this actually is an individual signal. So
4 nanohertz is a long
yes,
time.
Yes.
So
not many cycles.
that gives you a scale and you have an amplitude. So what does that imply for the mass and distance?
Well, unfortunately, the mass, we're just not getting any information on the mass right now. It's at such low frequencies that the way that we get the mass is actually that, so the time scale over which these signals is changing is certainly not within 15 years. You cannot measurably notice the change. However, the pulsars are typically thousands of light years away, right? So we're typically seeing the signal from the pulsar, there's a perturbation to the pulsar, and that's from about 1,000 years ago. And so the difference between the frequency of the wave at the pulsar to the frequency at the Earth then tells us the mass of the system. But these are at such low frequencies that we can't even tell that for these ones. There is no difference between the pulsar frequency and the Earth frequency. So we've got no information of the mass. We would have information about the mass if it was, say, a 10 or a 15 nanohertz system. But we have no constraints on the mass at all.
But I guess I just ask it right around, you could construct and say, could I detect such a thing just to begin with, would require it to have a certain distance.
That's right. But we can't, if we can't get the mass, we can't get the distance with gravitational waves. So this is definitely plausible. I mean, in these simulated models of the universe we get things like this. So it's not crazy. In fact, in the simulations we did, we found a signal like this should occur, actually, strangely enough, exactly at this frequency. This is the most likely frequency that we predicted. We put this paper out significantly before any of this work, right? So we actually put out a paper predicting what would be the most likely system. It was exactly at this frequency, and the mass was around 10 to the 10 at around a gigaparsec. And that should happen in all the different simulations, realizations we did about 10% of the time. So it's a bit unlikely that we're seeing it, but only 1 in 10. If that was a lottery, you'd buy that ticket, right? For the 18-year analysis, we're predicting that there's a priori, before we have this result, it's about a 30% chance we should see one. So it's not crazy that we might be seeing an individual system. Lucky, but not crazy. And going forward, we now have CHIME is being used, the timing. We're also using Meerkat. The Chinese have FAST that's doing an incredible job timing a whole bunch of pulsars. We've got beautiful results from Meerkat already. Eventually we'll have the SKA. So that's sort of where the future goes for pulsar timing. There's a lot of big telescopes or combinations of lots of medium-sized telescopes getting used. And so I think as we go forward, you're going to be patient. This is going to be tens of year timescales, 5, 10 years, except we will have an answer, I think, on much better picture about whether we've actually seen a background will all happen in the next year or so, because we have a lot of data already, right? We have the combination, and we also have data in the CAM we haven't analyzed. So you don't have to wait 10 years before we can give you an answer. I think maybe in a year or so, we'll have a much firmer case of whether we've really seen something. Have we seen an individual system? Those answers are coming up soon. You don't have to be that patient. But this is decades of observation still to go. Finally, heading to space. So this January, the LISA mission, which is Laser Interferometer Space Antenna, it's a European-led mission with NASA participation at around the 20-30%, It's up for mission adoption. They have a different system in Europe, but it's in NASA parlance, it's going to phase B in January is what we expect. So, you know, it's really starting to get going. And it's going to be this, this isn't quite to scale. The satellites are only about 2 meters across and the Earth isn't quite that big compared to the sun. But about the one thing that actually is to scale here is the size of the sun to the size of the array. These are 2.5 million kilometers apart. It actually has twice the collecting area of the sun, right? So it's a big detector. It's working down in the millihertz range, so between pulsar timing and the ground-based detectors, and orbiting around in a Earth trailing orbit. The capabilities, this is one of those future ground-based detectors, Einstein telescope, detecting black holes between 10 and 1,000 solar masses, say. LISA detecting black holes between, say, 100 and 10 to the 9 solar masses, all the way out and beyond redshift 20, right? So deep into the early universe. So potentially probing black hole seeds. These are the signal to noise as the color bar. Obviously, the closer systems and the heavier systems have higher signal to noise up until a point, because once they get too heavy, they merge, you know, before they even get to the LISA band. That's why it starts to taper off here. And so again, we're looking for these mergers happening over cosmic history. And, you know, I'm excited by some of what's been coming out in the early results from JWST, from this paper, for example, this year. Evidence for many low mass black holes at very, very high redshifts, including in this case, they had a few candidates that look like maybe dual AGN systems. So there seem to be, if the interpretations are correct, there do seem to be quite a population of black holes in these early galaxies. And hopefully, if there's dual systems and enough gas around, they'll get together and form binaries. So I think the prospects for LISA look very promising. They haven't yet. I was talking with some of my colleagues who work on the modeling of these populations, and no one's really yet, because it's so new, what's coming from JWST, and there's all sorts of selection effects. They're obviously seeing them with these more massive systems. But what's this actually going to mean for the sort of expected rates for the LISA detector? You know, are we going to see, you know, a few black hole mergers a year? Are we going to see hundreds? We just, you know, we don't really know yet. But this will help, I think, give us some guidance on what to expect. So far, the history of gravitational wave astronomy has been, whatever the theoretical prediction has been for the rates and everything, it's always significantly undershot what we've actually found. So it's always been, everything's always come out on the absolute highest end of any theorist prediction. So I think people have been a little bit too cautious, maybe just because we've never seen gravitational waves. So I'm hopeful at least we'll see a lot of these high redshift black hole mergers. And, you know, here's the sensitivity for LISA down this millihertz range. We're going to have all these signals. But the thing is, you can see that even a black hole signal is going to be in the sensitive band of the detector, especially for the lower mass systems, for like a year or so. We have a whole bunch of binaries in our galaxy, millions of them. They'll just be continuously on. There'll be these so-called extreme mass ratio in spirals, or EMRIs, which is a sort of stellar mass kind of black hole orbiting around a sort of 10 to the 5, 10 to the 6 sort of solar mass black hole like we have at the center of our galaxy. And these signals are all on continuously. So it turns out you actually have tens of millions of signals simultaneously being detected. With LIGO, we get one, wait a day, a few days, get another one, right? So we just analyze one, analyze the next one. Here, millions of signals constantly. And so we have to separate them. And so my group works on that problem. And this is just a tiny fraction of all the signals we might expect to have. And in our simulated analysis pipelines we've been developing, and we have to do what's known as a global fit, simultaneously fitting for tens of thousands of signals. We can't get all millions of them, there's just no way. But because they're just, some of them just aren't loud enough and they're confused. But we're now working, we're currently up to a 20,000 parameter simultaneous fit for, that's the number of parameters that we're fitting simultaneously in a giant transdimensional Markov chain Monte Carlo analysis, right? We've been running these on Amazon web service and clocking up a lot of bills there. But yeah, I think we think we'll be ready. You know, here's another. This is one simulated data sets. We've got all these black holes merging. The green is the galaxy. It's modulated because as the detector sweeps around it, it's either sort of pointing more towards the center of the galaxy or away. And so we've got all these signals. And here's the modulation. So as the LIGO detector sweeps, here's the galaxy emitting in all these white dwarf binaries, for example. And then occasionally it sweeps right across the center of the galaxy and we get a peak and then a secondary peak where the red's the most sensitive part of the detector. So we've got this modulated galactic foreground that we have to deal with. And but still we're able to pull out, this is in galactic coordinates. These are all of the whole bunch of the white dwarfs and then various different black holes from simulated data that we just blindly are able to pull out with our simulated analyses. So we're working on this. We've still got about 10 years to finish, you know, getting the analysis ready. We still don't have any way to detect these extreme mass ratio wind spirals, which are some of the most exciting because they're really complicated systems. Sam Gralla here has worked on this kind of thing. So here's showing the last day of a small black hole and where it spent its orbit. Notice they're highly non-Keplerian. You'll notice a couple of features in this. Here's the waveform going across. So we're getting tens of thousands of cycles, but once in a while, you'll sort of see it, the pattern kind of like makes like a coherent pattern, and that's various resonances. So unlike in Keplerian motion where the radial frequency, the azimuthal frequency, and the equatorial frequency are all the same, in general relativity, they're all three different frequencies. And so there are times during the as it loses energy and angular momentum to gravitational waves, it goes through various resonances where some of those frequencies are commensurate, and then you get a jump in the emission rate. And so there's all these sorts of interesting features that happen in these waveforms, making this beautiful map of the supermassive black hole. Maybe use it to probe like any gas or stellar perturbations in that area, but also great for doing, say, tests of general relativity, I think, because especially things like, I really think we can't actually model these jumps very well in general relativity yet, but once we can do that, I think that these, because these are these resonances, it's an amplification that's happening. So if there's a small deviation from general relativity, it could be also amplified right at these resonances. So I think that if it could be a good place to look. And you know, quite a few years ago, Scott Hughes and one of his students actually showed that generically, each one of these passes through several resonances during the time that it's being observed by LISA. So we should see several of these resonances per system, and each one of them could have interesting information about, you know, is it, because every test we've done so far, general relativity is completely consistent with everything we've seen so far in gravitational waves. So any departures from general relativity are going to be down in the sort of, you know, parts per million maybe. And so to see that, I think we're going to need systems like this where we're seeing hundreds of thousands of cycles with interesting things. And I see I have a final question, but I'm just thinking, it's my final slide and I'll get to your question. You know, if you think about the history of, say, optical astronomy going from, say, 37 millimeter Galileo's telescope to 39 meters with like these ridiculously new, ridiculously large glass that's being built. You know, so 400 years from now, gravitational wave astronomy, if we're still around as a species, I don't know where we'll be by then. But thank you, and I can take some more questions.
Very beginning slides, you said in the GW15
Yes.
signal, there's a kind of show there's a time delay
Yes.
between the gravitational wave signal and the optical signal.
Oh, 17.
The 70.
Yeah, like the
1.7 seconds.
yeah 1.7 seconds. You mean for the binary neutron star?
Yeah.
Right.
So
Right.
so what was the interpretation of that?
Well, I bet Vasilis or someone could answer that better from what so it's this is a off-axis gamma ray burst, right? So we weren't seeing like the gamma ray burst jet, if there was one coming at us. We're seeing kind of through the obscuring torus. And so I guess there was, some delays in getting the signal out through the materials. And there's going to be a little bit of a delay just in terms of they're thinking that, the things that are generating this signal, but that time delay should have been quite a lot shorter than 1.7 seconds. So I think it was geometrical effects in the obscuration and
Yeah, there's a little bit of everything.
Okay.
First of all, you form a neutron star. It's not a black hole.
right. And then
And
so it's a hypermassive.
That neutron star, there's a delay time for it until it collapses to a black hole, and then until you launch the jet. And then the jet has to break out of the cocoon that is around it, and then you'll start to see the gamma rays that are coming out. So that's where all this 1.7 seconds is.
I see.
I think it was a lot longer than what people, before this was seen, it was definitely a lot longer the delay than what people had been talking about, right? So people had talked about quite a lot shorter delays. We're expecting, 0.1 or 2 seconds, so it was surprising
Yeah.
that it was quite a lot longer than, what people had been sort of, at least the common law that I'd been hearing before we actually had this event. But even with that, let's just take 2 seconds, right? This event was, what was it? 40 megaparsecs away, right? So, 120 odd light years away, whatever the number is. And so if you think about the photons and the gravitons arriving within, say, 2 seconds of each other, forget that there was any delays, but just put 2 seconds, that still means that the speed of light and the speed of gravity have to be the same to parts in 10 to the minus 15, right? So this was that particular, it's not this one. Oh, you don't see anything.
Or if photon or graviton have mass, yes.
That's right. Then there would be and that allows us to put constraints on the mass of the graviton as well, right? Well, that's actually, yeah. So that's
Well, you need to have a massive theory of gravity.
right, mass theory of gravity.
People have done that.
Yes.
So
So
you can have massless theory of gravity, get a constraint of photon mass.
yeah, so it actually eliminated a set of alternative gravity theories.
Okay.
So some did,
Kill the whole industry.
yeah, kill them. I mean, not the entire industry and industry. There's still plenty others out there. Right?
Sub-industry, yeah.
A sub-industry of alternative gravity theories was immediately wiped out, which is what you want observations to do, right? That's what Sam sounds like he wants all of them wiped out.
Are they're not able to push some parameters to.
No. No, it's like it was like a key part of
So
some of
just
those
completely
theories.
directly.
There's plenty of other alternative theories that don't predict, that there would have been a delay, but it got rid of a good chunk. Yeah. I promised I would come back to this question, then I'll try and get to others as well.
Yeah, for your MREs, I was just curious why you need to have a stellar mass black hole if you're dragging around a neutron star or
Oh
a
yes,
white
no,
dwarf
totally.
or a regular star. I think it would do pretty much the same
Yes.
thing, wouldn't it?
Absolutely. It's just that, in fact, I don't know how to make this come back. What am I doing?
It might even be more likely that you see one of those.
Right. Actually, it's much more likely if there were intermediate mass black holes, say, of 1 to 300 solar masses, we'd see those, they'd be much louder signals, right? So the reason that we sort of think, well, we're thinking just because we see so many 30, sort of 40 solar mass black holes in LIGO, that seems like one of the best candidates just because there's just so many of them, right? But if there are some intermediate mass black holes, even if they're up to, 10 to the 3, 10 to the 4 solar masses, they'd still behave much like an emery.
If I was thinking the other way around, those sort of.
Oh, and neutron star works as well. The trouble is the signal goes down with the mass, right? So it just gets weaker. It could work with white dwarfs. People have, considered the possibility of white dwarfs. And then with a white dwarf, you could even imagine some of them might pop, right? And then you get a disruption that goes along with it. But the problem is the white dwarfs, so much less mass and, it scales so heavily with the mass that the range to which you could see them is so much less that we just don't think. So we think that just based on the population and and how far we can see them, it's going to be dominated, we expect to be dominated by 30, 40 solar mass black holes going into. But then again, who knows? Like there's these scenarios that say you can form black hole binaries in the accretion disks of supermassive black holes, right? So who knows what's exactly going to happen there, but
Andrew?
I wanted to ask a question about the fortuitousness of the binary neutron star merger.
right,
And, you know, that ahead of its time
yes,
factor. And it seemed to me like you were saying that part of the reason was that Virgo was online and capable of, in this
Yes.
case, not detecting it.
Right.
So is this a question of sensitivity or of localization?
mostly localization,
Right. So
Right.
if you had an efficient enough search strategy
right,
and you were able to, you know, even if you only had the LIGO detectors
Right.
and you have a large area, but if you had an efficient enough search strategy,
That's
you
right.
might still be able to find.
right. So some of these sort of wide field, like things, that's what we mentioned, things like ZTF and whatever, which is looking at, you know, and they have search strategies they've already developed for various kinds of transients, right? So you know, yes, it's not like it's impossible, but I think the predictions I was showing, which I don't want to fiddle with my computer too much to figure out to make the screen come back, but the predictions I was showing were I think assuming that we had Virgo operating at some sensitivity and that sort of thing, right? So factoring in how well localized each of the events might be. But you know, unfortunately, Virgo had some breakages, and they haven't really been able to kind of get up to the sensitivity they would like. So they've been trying to decide what decide what to do. Is like do they rip everything apart and fix everything really like they needed to, which would mean there'd be no hope they would ever join the fourth observing run, or do they just kind of soldier along with a half-broken instrument and try and do the best they can, which is what they've decided to do for now. So we're just lacking another comparable sensitive detector for really getting great localization, anything like what we had with.
But in 04, it is likely that that LIGO will be detecting
Yes,
events, and then the question is whether anyone will be able to follow them up.
right. The other thing is,
Electromagnetic
yeah, right.
spectrum efficiency.
That's right. I mean, we're extremely lucky about how close that event was, right? You know, we actually, as you start to go out to more, you know, typical distances, the number of telescopes that can actually pick up a kilonova really starts to drop, right? So it's just, I think
Yeah. Well,
we got spoiled by that first event. It was so close.
there's a not quite theorem that says that the first thing that you detect is often unusually bright.
Yep.
All right, Andrew, and then Himansh.
Yeah, so maybe you could say a little bit more about the nature of those resonances. I mean, in particular, is this like right, a resonance between two individual bodies, or
No,
your image seemed to be
No,
like it was
what's actually resonant here is
Still.
the we have these like these three frequencies going right in the system, the radial, azimuthal, and sort of equatorial frequencies. Those just come to be commensurate, like integer ratios at these resonances. Now, a Keplerian binary is always
not those frequencies for any individual or
no. This is just for the
cloud.
well, no, it's just one binary.
Yeah.
Right, but it has three frequencies. Actually, it has even well, it has it depends what you call an orbit, right? Like it's completing a radial. I mean, perihelion precession is when you complete one radial cycle at a different rate than you complete your azimuthal cycle, right? So that's what. But these also have, in terms of the out of plane, there's the frequency that you bob up and down that way, and that's also, well, the frequency you're going in the azimuthal is also different.
Okay, so I mean,
sorry,
that's true for
equatorial.
planetary and stellar dynamics as well. Right? Bodies are not
Right,
processing, and that's what causes the resonance.
but that's like multi-body effects. In GR, it just happens just purely, for a two-body system.
for sure. But so it's then a single orbit that's
Yes.
in resonance
Yes.
with itself?
Well, it's
Or
the,
with
I mean,
project?
it's the resonance affects the emission. Right, so the fluxes of angular momentum and energy. And so you get a, you know, a sort of you jump almost from one frequency to an X because there's kind of a, almost like a little burst, if you like. So it's not just the steady emission, you get this.
You have a non-isotropic gravitational field, right?
Well, no, to leading order, it's just that of say, a curved black hole with a small perturber. So
But
it's
a Kerr black hole it's not spherical.
no, it's azimuthally.
Right, so I'm making the analogy to something that happens if you have, say, an object orbiting in the gravitational field of like the galaxy disk or something like that. So it's not isotropic, so then you get resonances that are couplings between, say, the radial and the vertical frequency, that kind of thing. So you just have one object and yet it's got resonance.
Right.
Andrew, are you happy?
Sure.
Himanshu?
So you talked about the cavity and light bouncing around the cavity.
Yes.
So, and you mentioned that you can get the effective flux to any cross section to be a megawatt. So since it's just light bouncing around, what prevents you from getting more? And
Oh, because
if you get more than one to reduce your.
We
quantum
only,
points.
that's the finesse of the cavity, right? So you eventually, on average, the average photon's doing something like 100 or so, maybe it's a couple of hundred bounces, right, before you lose it. So it's not like they're there forever. You
Okay.
sort of so the storage, is time. I mean, these are very high finesse cavities, but it's not infinite. So there's some leakage basically, and so it's sort of you can only sustain a certain power.
Okay.
I had a question. You mentioned with the pulsar timing arrays that for 4 nanohertz signal, that there's like, this was a very unusual thing because in sort of LIGO, we're used to the idea that like, as soon as you have like a signal and you have its frequency, of course you have an amplitude. So then you have, what you need to do is
Right.
describe. You pointed out that there's a sense in which in nanograv, you're, at least for that signal, it's so low frequency that there's some way that you can know what its frequency is, but you can't really know what the amplitude is. And so I'm wondering if is that essentially
You have
because
the amplitude, you don't have the distance, right? The
don't have the
amplitude
distance.
is
Oh,
given
yeah.
by the product of the chirp mass to the 5/3 power, the
Right.
frequency to the in time domain 2/3, and then you've got the luminosity distance on the denominator, right? So there's
okay.
you have the frequency.
Yeah.
So you have the amplitude, right?
Yeah.
And you have the frequency, but you need the chirp mass, otherwise you can't solve for the distance, right?
Right.
Because
okay.
you've got the combination
Okay.
of chirp mass and distance. So you've measured some combination. You've measured the
Ah.
chirp mass to the 5/3 power divided by the distance. You've got that.
Yeah.
But that number's pretty useless, right? Because you
Is
want to
that-
know.
That was the question I was asking. I mean, if that's a product, it seems, you can get, an incredibly bizarre, unbelievable mass at a large distance, or
Right.
an incredibly
That's right.
puny mass close by, but
Yes.
somewhere in there has to be a reasonable
That's right.
answer, and that's more what I was.
Right. And
after.
I'm saying that signal is completely reasonable if you look at, simulated populations of supermassive black holes from these, either using like cosmological simulations or various other prescriptions. This kind of signal, with a kind of mass we believe that supermassive black hole binaries can reach, and the kind of distances where we'd still be expecting to see some. This is totally a reasonable signal. There's a combination of mass and distance that's completely within the realm of pretty much every simulation out there. So
I agree. I mean, we know black hole masses from 10 to the 6 to
Right.
over 10 to the 10th.
Right.
Are all of those possible to create that?
it's going to be at the higher end most likely, because unless it's stupidly close, and then
Yeah.
that's highly unlikely just based on we just don't have is there a big galaxy that close, like, I think that it's much more likely to be, just because the volume, of course, grows cubic with distance, the chances are it's a bit further away and then high mass. I mean, that's what we see when we look at the simulated populations. It's, it's that sweet spot, right? Because if they get, you go further and further away and you get more and more of them to a certain point, but they're getting weaker and weaker, right? So there's this sweet spot where it's right around, gigaparsec or a few gigaparsecs, right around there is where you got that balance between the signal being strong enough and there being enough of them. So the probabilities that it's probably, but we don't yet have, and it's unlikely that we'd be able to measure this change of frequency for such a low, since the frequency is so low, the chirp timescale goes the frequency to the 11th. That's power. Yeah, so it's a high power frequency, right? So the time scale, the f dot, it's a f to the 11th third. So it's it's better than cubic. So it's almost quartic. So it's a very strong function of frequency. So these low frequency ones really just aren't evolving very quickly. So it makes a huge difference going from 4 nanohertz to 10 nanohertz. And so a 10 nanohertz signal, we can constrain the masses.
Thanks for following correctly.
I mean, like 12 minutes after. Well, I suggest if you have any other questions, you can just, ask Neil. He's gonna be here for a few more minutes. So let's all thank Neil again.